So I want to talk about a little idea from complex systems theory, which is going to revolutionize technology as far as I can see. I think it's going to completely change the way that people make stuff. The idea is really quite trivial. It's just that there are a lot of very, very simple processes or rules which can create immensely complex patterns and dynamics. In other words, there's lots of cases where you just put a little bit in and you get a lot out. This pattern you're looking at, for example, it was generated just by like one line of computer code. And I could talk about the philosophical implications of this till the cows come home because I think it's fascinating. But actually, I'd rather just get down to brass tacks and show you some real applications of this new kind of approach towards making technology, specifically for wireless networks and for 3D printing. Okay, so like I say, I believe we're in the early stages of a kind of technological revolution. And I think that the guy that did more than anyone else, perhaps, to start this revolution was Stephen Wolfram by writing his epic book, A New Kind of Science. And the sort of approach he takes is very nice and elegant, the way he begins, because he begins with a very simple question. How do small, simple programs run? Not word checker programs, not Windows, not stuff that people have coded up for themselves, but just like small random programs. What kind of behavior do they have? This is what he asked. And so he started out by looking at a class of programs called cellular automata. Very simple. The idea here is that in this picture, you have a row of black and white cells and you have an update rule. So successive rows going down show this pattern evolving over time as the rule is repeatedly applied. In this case, the rule just says that a cell is going to become black if it was black before or if it was next to something that was black before. And you can see that the rules are kind of shown in the little pictogram at the top. Okay, so these are the kind of simple programs which he started investigating. And the real brilliance of it is that he did it systematically. He didn't just look at this program, that program, and the other program and then stop. No, he listed all the 256 different possibilities and he looked at the dynamics of every single one. And that's how he discovered these things, which I think are going to have a great impact on stuff. Here's another cellular automata. It has quite similar rules, but slightly different. You can verbally describe it saying that a cell's going to become black when both of its neighbours had different colours on the previous time step. Otherwise, it'll become white. Or you can just see what the rules are just by looking at the pictures. So, what's going on here? Well, we're starting off from a simple initial condition, but it's funny, we're getting really quite an elaborate pattern. It seems sort of slightly surprising that so much, that such an intricate pattern can emerge from such simple rules. But then again, this is basically just a fractal pattern. It's just nested triangles. It's not exactly a really hard shape to understand. And so I guess it's conceivable that such simple rules could create such a thing. But this is where intuition breaks. This rule is only slightly different to the last one. It's called Rule 30. And again, we're starting off from a single black cell. And look at the pattern that's coming out. We're just following simple deterministic rules. So why is this pattern so complicated? There's no random number generator here. There's no source of randomness at all, except just what's going on intrinsically in the way the system's running. So when most people see this, they say, well, surely there must be some hidden order here. What about if we run the system for longer? Do we see some order now? It looks more complicated than ever. And people have done a lot of analysis on this, and nobody's found a way to mathematically understand how the system works or predict its future. And also, you know, the central column of cells, black and white cells, the order of those is like random. I mean, there are tests to see if a sequence is random or if it looks like it's randomly generated, and this passes all the tests. This system really seems to be generating proper pseudo-randomness. And it's doing all this just from following these tiny little rules. So this is what Stephen Wolfram says really sparked his interest in trying to understand how simple programs run. And so he looked at many different kinds, not just cellular automata, but Turing machines, substitution systems, tag systems, continuous cellular automata, differential equations, systems based on, this one is just powers of 3 written in base 2. Look how complicated this pattern is. There's an immense list of systems that you can find which have this property that the rules are really simple, but the shapes that are made are elaborate, complex, possibly pseudo-random, and, you know, with the potential to have some really great applications. And this is what this whole idea is all about. It's really a new approach to computer science, if you like. I mean, a lot of people just call it NKS now because that stands for a new kind of science, which is Mr. Wolfram's book. I think he used to call it computational naturalism, which I think is maybe a better name, because really what we're looking at here is the kind of study of what programs do in the wild when they're not tamed and controlled by people. And what we find is that they do very, very interesting things. Anyway, there's lots and lots of things, you know, philosophical and scientific implications of this. Lots of stuff that you can model, like things in nature. But I don't want to talk about that today. I want to talk about some specific technological applications of these ideas. So what I want to do is to show how these kind of NKS ideas can be used to make some new progress towards some important problems related to wireless networks. Because it's actually a very critical time now in wireless networking, because the number of mobile phones is increasing exponentially, and basically it's a resource sharing problem, because two people who are near each other, if they use the same frequency, then they interfere with each other, degrades their quality of service, right? So there's only so much spectrum to go around, but there's loads and loads of users. So we have a resource allocation problem. And my question that I'm interested in is, can we use these kind of ideas about searching through and looking what simple programs do to help us with these kind of resource allocation problems? And so in particular, to begin with, I looked at a really idealized case. So in reality, wireless networks are very complicated. I mean, you know, your different devices are different distances away from each other. They have different amounts of power that they'll use, different frequencies. All of these things affect exactly how much interference they cause each other. But the basic goal of the wireless engineer is always the same. They just want, you know, everyone to get good quality of service. So what I did is to look at a really simple kind of, idealized model of a wireless network. Really simple. In fact, most people would call it a load balancing problem because basically all I'm trying to see if I can do is to get a load of individuals to naturally spread themselves evenly across a load of resources. In the context of wireless networks, this would make sense in certain scenarios, like if you had a lot of people living in close quarters and there's only a certain number of channels for them to use, which are the same as each other, then the best thing for these users to do would be to, spread themselves evenly, like say have 5 guys using each channel, something like that. The issue though is how do you arrive at a situation like that? How can wireless users organize themselves into these near optimal configurations for sharing resources? Well, somebody had a very bright idea a few years ago called cognitive radio, which was some idea about how um, about being able to equip wireless devices with the capacity to scan and switch channels. But the thing is with cognitive radio, well, there's a few issues with it, but one of them is that it's a very expensive and very kind of it adds a lot into the system. There's a lot more technology there. A lot more things can go wrong. There's a lot more other things you have to consider. You have to consider the fact that people are going to be um, you know, are they going to be scanning things fast enough? Are they going to be finding opportunities fast enough? What are the dynamics going to be like? So cognitive radio is a promising lead, but I think with this, with these kind of NKS methods, I'm not saying I've solved any great problem, not at all. This is very early stage research, but it does seem as if there might be a glimmer of hope of finding something, a solution which is quite a lot, which has quite a lot less overhead. So what I'm talking about here is minimalism. You see, that's what NKS is great for. It's all about simple programs. And so the question I ask is how, what's the minimal amount of sensitivity and intelligence a wireless device needs, or wireless devices need, to be able to work with each other to share the spectrum? In other words, how dumb can things which can do load balancing be? We want them to be as dumb as possible because then we don't have to pay loads of money to add in sensors and scanners and things like that. So basically, it's a question of how can we make a system where a load of wireless users can organize themselves across a load of channels um, without communicating with each other, without knowing how many other users there are, without being aware of exactly how much congestion they're facing. These kind of things. We want our users to have very little information and yet still be able to organize themselves and do load balancing. So this is what I was investigating. Um, and so to look at this, I looked at a certain class of systems, and there was two assumptions. So before I talk about the systems, let me just talk about these two assumptions, get them out of the way, because these are the two, possible holes in the model. One is that we say that the users, who are all similar kinds of wireless device users, we say that they're going to get chances to update their channels asynchronously in a cyclic order. So first user 1, then user 2, then user 3, then user 1, then user 2, then user 3, like a clock. These users get they do their updating asynchronously and cyclically. Now that seems like a kind of okay assumption, because we could do that with technology. I mean, the users wouldn't have to communicate to set something like that up. All they'd have to do is have clocks which have the same period and start their clocks off at random times. And chances are you end up with a system like that where people would update in such a sequential manner. The other assumption is a little bit harder to justify, but not impossible. Basically, the way these systems are running, and I will describe the dynamics in a minute, but this the way they are is that all of the users start on the same channel and they all start in the same state. And then there's some dynamics, and the idea is that these dynamics pan out and end up with load balancing. So the thing that people might question is, well, isn't it unrealistic to expect that in a wireless system all of the users will be on the same channel and in the same state? And the answer is yes. If you just take a snapshot of a real system, of course, that's not what you'd see. But the thing is, we're dealing with deterministic, low information algorithms. And for those kind of things, um, I think you kind of have to reboot the system sometimes. Maybe I'm not making much sense. What I'm saying is that um, the way we can make this kind of thing realistic and practical is to say that periodically the wireless network can reboot. Let's say every morning at 8 o'clock, all of the users in the vicinity, they all switch back to channel 1 and all reset their states. And then the system reorganizes into a nice resource allocation. So we can do this. We can do this rebooting where things go back to square one and then resource allocation occurs again. And I think this is possible. And from what I was saying before, I think it's probably even necessary if we're insisting upon these kind of deterministic low information procedures of resource allocation. Anyway, that's all the hand waving and trying to defend the models over with. Let me now talk to you about what is actually going on. The exact same discussion and ideas will apply to lots of other resource allocation scenarios, like cars choosing lanes to drive on and so on. But for the sake of discussion, I shall talk about channels instead of resources, and I'll talk about wireless use. Okay then, so I'll explain how this stuff works. The users, so in this particular case, like we'll talk about more general Okay, so the idea generalizes quite easily, so I should just explain this example. So in this case, there are 3 different states that the users can be in. State 1, state 2, and state 2 grey, the grey circle. So these correspond to the right, left, and middle nodes shown in this picture. And the thing is that our users update in a cyclic order. So, like a clock, what user 1 gets to change their channel, then user 2 gets to change their channel, then user 3 gets to change their channel, and then user 1 gets to change their channel, 1, 2, 3, 1, 2, 3, 1, 2, 3. So they update in a cyclic asynchronous way. But the thing is that the users have very little information about what's going on. The only thing they can tell is whether their congestion level increases or decreases at a given time. So maybe they can't count, but they can tell when their congestion level is increasing or decreasing. For example, I mean, I might not know much about how my radio works, but I know if the quality of, if I'm getting a lot of interference on my radio show when I walk into a crowded room. I don't know how many people there are there, but I know the congestion level increased. Well, these folks are a bit like that. They can detect changes, but they can't necessarily count. And the thing is that they respond to these changes. In particular, so at a given time, one user will switch channels. And when that happens, let's say they're switching from channel A to channel B. Well, when that happens, every other user of channel B is going to experience an increase in their congestion level. And the way I design these systems is that when they experience an increase in their congestion level, they will change states. In particular, they will change their state from their current state by following the red arrow. Well, the arrow with the red plus sign on. It's maybe hard for you to see. But if you look at this diagram, there are these three different states, and say you've got a user who's in, well, let's say the grey 2 state, and let's say somebody switches to their channel. Well, in that case, they are going to change their internal state to 1, okay? And that's the way these systems work. When a user's congestion level increases, then they change their internal state by following a red arrow with a red plus sign on it. When their congestion level decreases, they change their state by following an arrow with a blue minus sign on it. Okay, so to avoid confusion between states and channels, I shall refer to the states as 1 white, 2 white, and 2 grey. They correspond to the right, left, and middle nodes on the state transition diagram at the top. So there's 3 different states: 1 white, 2 grey, and there's also 2 channels. Okay, so let me talk you through how the system runs. The diagram shows the system running over the first 6 time steps. And to begin with, all of the 4 users are on channel 1. So there's 2 columns, they represent the 2 different channels. And the column the user's in, that shows what channel they're using. And I'm using superscripts to represent the states that the users are in, their internal states, which sort of represent their inclination towards switching to different channels. Okay, so time begins, and user 1, there's 4 users. User 1 is the first to update, and they're in state 2 grey. Now all the users start on channel 1, but user 1 is in state 2 grey, which means they have an intention or inclination towards switching to channel 2. And so they do, because it's their turn to do what they want. And then what happens? Well, then users 2, 3, and 4 experience a decrease in their congestion levels. And in response to this, they change their internal states. You can see how exactly that works by looking at the state transition diagram at the top. In particular, when a user experiences a decrease in their congestion level, they change their internal state by following one of these kind of blue minus sign arrows. So if you look at the diagram, you'll see that user 1 switching away causes the other users to go into internal state 2 white. Okay, so I'm calling these states 1 white, 2 white, and 2 grey. Okay, so that's what happens on the first time step. What about user 1? They switched away. Does their state change? For the purposes of this discussion, no. Let's just assume that the guy who updates, they change their channel, but their internal state stays the same. And also you can ignore those green arrows on the state transition diagram. Okay, so then we go across with the black arrow and we see the configuration on the next time step. We have users 2, 3, and 4 on channel 1. They're all in state 2 white. And we have user 1 who's on channel 2 who's in state 2 grey still. So then what happens? Well, it's user 2's turn to update because they're updating in sort of a sequential cyclic order, and they're in state 2 white, which means they want to switch to channel 2. So that's what they do. And as a result of that, the congestion level of users 3 and 4 decrease, and that causes them to switch states. And also the congestion level of user 1 increases, and that causes them to change states. And you can see the whole system progressing in this kind of way. To be honest, going through the details of it and working it out with pen and paper is rather complicated, I find. I mean, in this case, like, we find that after we run it for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 time steps, we've reached a load balancing situation where the users have spread themselves evenly across the channels and they no longer want to move anymore. But it took me a fair amount of time to draw these diagrams and work out exactly how this is going on. But it's fairly easy to code. I mean, conceptually, what's going on here is really pretty simple. It's just that the users have internal states, which represent the inclinations to go to different channels, and their internal states change in response to fluctuations in congestion levels. Okay, so here's another example of one of these systems. It works in a very similar way to the one I've just talked about. All the users start on channel 1, and in this case they all start in internal state 3 grey. Now, the key difference here is, well, there are a couple of key differences. One is that there are 3 channels instead of 2, and so, I mean, this is designed to do load balancing, but load balancing is harder when there are more channels. The other difference is that these green arrows, which I told you to ignore before, actually do play a role in this system. So you remember before I said we ought to adopt a convention that the user who actually switches channels doesn't change their internal state. The active user doesn't change their internal state at that time. Well, actually these green arrows allow us to generalize that. We can drop that assumption. So in particular, when a user updates, they will change their internal state from their current state to the thing that the green arrow from their state points to. So if you look carefully, you'll see that these green arrows are labeled with the letter U for update. So, to put it more succinctly, when a player switches channels, they change their internal state by following the U arrow. So in this case here, for example, if we have a user in state 3 white, then they may if we have a okay, so in this particular example, okay, so here for example, if we have a user in state 3 white and they update, then they're going to change to state 1 white. And what about the picture at the bottom? What's that about? Well, that's just another sort of picture showing how this system manages to achieve load balancing. Basically, the points in the triangle represent how many users there are of each of the different 3 channels. And this system, again, is a good load balancing system. If all the users run this particular simple little thing, then they can do load balancing. And in fact, it turns out that this problem can be solved in general. Okay, so it turns out that no matter how many channels you have, you can find one of these finite automata which is capable of achieving load balancing. So I think this is a fairly nice result, really. With basically, by taking this kind of simple programs approach, we find that we can do pretty sophisticated things with very, very, very simple little users who can't detect very many things. So here's an interesting system. We have 2 states, 1 white and 2 grey. And again, let's just say that everyone starts off on channel 1 in state 2 grey. Now, the rules of this system are really, really simple. The users update cyclically, like before, of course. And the way it works is just that when a player's congestion level increases, when someone switches to their channel, well, in that case, they switch their internal state. And when their congestion level decreases, they keep their internal state. So we've got this super simple load of rules and a totally trivial initial condition. And just look how complex these dynamics are. This picture here, this is what's known as a space-time plot. So if you read these rows across, the red blocks represent users of channel 1 and the blue blocks represent users of channel 2. So successive rows reading down, they show how the configuration evolves over time. And what's really interesting, I think, here is that we're starting off from a completely trivial initial condition, and our users can't even communicate with each other. And they're running by really simple rules, They've just got 2 internal states, and the only idea that they have is, well, whenever I feel more congestion, I'll switch states. That's it. And when I get a chance to update, I'll switch to the channel which corresponds with my state. That's all there is going on in this system. But just look how complex these dynamics are. They're pictured in this diagram here. Successive rows show the state of the system. So red blocks are users of channel 1, blue are users of channel 2, and time is going downwards, so successive rows show how the system evolves. So you see we're getting an immense amount of complexity here, and I think it's interesting for a few reasons. Like, it may be, I'm only really conjecturing here, but it may be that in very, very simple biological systems, where you have like single-celled organisms and things like this, which have to compete with each other, it may be that mechanisms like this are used to generate like pseudo-randomness and things like that. Because you can do this kind of thing by using a load of very, very simple processes. But it's quite beneficial for generating things like pseudo-randomness. It also has the lovely aspect that it's reversible. Here's another interesting uh, here's another interesting one of these, what I shall call congestion automata. Again, we start from the state where all the users are on channel 1, and we get some fairly interesting behavior. Now we get a kind of fractal pattern, and we're getting some fairly interesting dynamics, and we're also sort of exploring the space of possible system configurations. This is another thing that pseudo randomness can be good for. Here's another one. It's this one. It does load balancing, but not stable load balancing. And that might sound bad, but it could actually be good. So what I mean is that the old things I was talking about, they will evenly distribute the users over the resources, and then the system will halt at a fixed point. What this system does, again starting from a trivial initial condition, somehow using some kind of pseudo randomness generation or something, it manages to let the thing run so that the thing stays close to the place where the users are evenly spaced across the resources, but not in exactly that place. So it's kind of like a marble rolling around at the bottom of a bowl. It's not stationary, but it's pretty close. But that kind of effect could be useful in certain situations, especially if you think about, for example, some wireless networks and things. If you've got a lot of factors fluctuating, like new users coming in and stuff like that, it might be better to have a kind of shaky equilibrium where the system's kind of circling around randomly around the optimal point, rather than just having something which goes to the optimal point, but is like rigid and deterministic and um, could go wrong if another user enters the system, say. This is one of my favorites. So this system here, it's, I found all these things just by, searching through possibilities and making pictures. But what happens here, this is a system with three different, channels, I'm calling them, I suppose. And you can see the dynamics reading downwards in that picture on the left. And what's going on here, I think it's really interesting. We start off from this trivial initial condition where everyone's using channel 1, and the system sort of starts to load balance, and it gets kind of like so that the users are fairly evenly spread over the different resources. But then what happens is it carries on sort of changing in a pseudo-random way, and it actually ends up exploring a really large number of the different possible states that the system could have. So here we've got a case where it seems as if the system it doesn't just create pseudo-randomness, it seems to have a natural tendency to explore a large amount of the state space. So I wonder if this kind of thing could be useful for something like modular robots or something. I mean, it seems to allow um, a generation of a kind of random path through a 2D surface, and the whole thing is facilitated by a load of very simple elements which work together. So these could be attached together as some kind of modular robot, perhaps, or maybe even something in nanobotics. At any rate, just the existence of a system like this with such simple rules and such rich behavior, I think it's very remarkable. Okay, so it's quite remarkable that these systems can achieve such complicated behavior um, just by following deterministic rules and not really by communicating. Except they kind of are communicating a little bit because they're using congestion levels to send signals to each other in some sense. And so that's why I call these systems extroverted congestion automata. And so, yeah, okay, it's kind of interesting. These are pretty dumb devices that can achieve some pretty clever things like load balancing. Um, but the question is really, how dumb can you go? Is it possible to make devices which have even less sensory capabilities, but can still achieve things like load balancing? And the answer is yes. And another class of systems which I've sort of invented and been looking at, I call introverted congestion automata. Now, these systems are different to the previous ones in the sense that the users have absolutely no communication with each other at all, and they're not even aware of like when another user is going to increase their congestion level or something like that. These are very, very, very uninformed users. So the way these systems work, kind of similar to the way the other systems work, but you shouldn't get the notation confused because the notation is quite different. So let me explain. Okay, so when an agent updates, when they switch channels, they are going to change to a channel which is kind of suggested by their internal state, just like before. But what's different now is that it's the updating player who's going to now change their internal state. The other guys, they they're deaf, dumb, and blind. They they don't change their internal states because of the actions of others. But the guy that's updating, well, they're going to change their internal state depending upon the kind of stimulus they get as a result of their action. And it's really simple. Like, so say they're in state X. Note how every state in the state transition diagram, it has a like a red arrow with a plus sign on it, uh, green arrow with an equal sign on it and a blue arrow with a minus sign on it. So what happens is that if you've got an agent in state X and they update, if that update leads to an increase in their congestion level, then they change their internal states by going from state X along the red arrow. If the move leads to a decrease in their congestion level, then they change their internal state by following the blue arrow. And if the move doesn't change the congestion level, then they follow the green arrow. So you've got this really simple system where basically all the agents do is, um, follow what their state tells them. They do the thing that their state suggests that they should do, and then they alter their state in a deterministic way depending upon whether that move was good, bad, or neutral. So note now that this is really, really, really basic. I mean, you don't need much to be able to do this. Um, the the agents don't need to know how many other agents there are. They don't need to be able to count. They don't need to be able to know exactly what their congestion levels are. Um, you know, they don't need to communicate in any way. All they have to do is know how much they like the particular thing. So if you imagine it in terms of wireless users, um, it's very simple. You don't have to communicate with the other wireless users. You just see what kind of reception you're getting and follow some kind of simple procedure. And so this case here that you're looking at, this is the simplest um, introverted congestion automata that solves the load balancing problem when we've got two channels. Okay, so this is how this one. Okay, so this is how this one works. This is the simplest. Um, this is the simplest introverted congestion automata that can solve the load balancing problem when you've just got two channels. And the way it works is really simple. Um, Basically, your agents are going to update asynchronously in a cyclic order, just like usual. And the only rule is that they have this internal state, which is kind of like a target, if you like. It's an intention to switch to a particular channel. And, well, what happens is that whenever they arrive at a channel which is more congested than their old one, they change their targets. You know, they went to a place they didn't like it, they want to go back. And that's pretty much all there is to it. There's no other scenarios within which users change their states. And so it's a very, very simple idea. And, well, yeah, it works. Things start to get more interesting when you look at cases with more channels. This is a system I think is very fun. I wanted to find the absolute minimal system which can solve this load balancing problem when we have three channels, introverted automata. So it's like before. Uh, all the agents start using channel 1 and they start in this sort of 2 grey state. And this system here, it just so happens, always solves this problem. So even though there are 3 different channels and things can get quite complicated, if the users follow this very simple procedure indicated by this, which basically just tells them how they should react when they feel different changes in their own congestion levels. Well, if they do that, then they can do load balancing. Now, suffice to say, there's lots of other interesting complex dynamics that you can induce with these kind of introverted automata. But in the interest of saving time, I'll move on to something else a bit more technology related. So, like I say, one of the reasons I got into this was because I was interested in wireless networks. And real wireless networks are more complicated than just the load balancing problems because there's a spatial aspect. In particular, only nearby wireless devices can cause congestion to each other. So rather than the load balancing problem, which is really a fairly simple problem, given a number of balls, how can you evenly distribute them across some boxes? Well, the sort of spatial version of that, which is pertinent to the wireless networks, is given a particular network and given some channels which are available, what's the best way to allocate the channels to the users to minimize interference? And let's define interference as the case where we have a pair of linked users or nearby users who are on the same channel. So it's kind of like a graph coloring problem, kind of like a generalized graph coloring problem. We have a certain number of channels we can give to our users or vertices, if you like, and we want to minimize the number of edges that have both terminals of the same color. Can our computational naturalism ideas help us here? Well, I did some experiments playing around with some codes involving lots of different kinds of updating mechanisms and rules. And in particular, I started to look at ones where the agents would have a kind of memory of what state they were in before, and they would update in the order of degree. And I found out that there were some algorithms which really did seem to behave quite well.
Okay, so that's a little bit about potential applications of these systems to wireless networks. What else could they be applied to? Well, I think one of the most obvious aspects of many of these patterns we've been looking at is they're quite pretty. So why not see if we can make some objects out of them, 3D print them? I mean, here's a kind of diagram which shows some difficulties with creating new technologies. I think, in general, there's often two reasons why people can't make new technologies. One is they don't have inspiration. They don't know how to do it or what to do. And for that, I think this whole kind of mining the computational universe thing is really useful. And not only because it gives you loads of new solutions, but it exposes you to loads of new effects, which probably inspires new technologies, just like when we saw birds and then we wanted to make planes. The other thing that stops people making technologies is a lack of proper tools, the inability to actually create the complex forms envisioned. And to solve that one, 3D printing can come in. 3D printing can make loads of cool stuff. And so, specifically, I want to talk about some applications which connect these two things. So, architecture is one of them. There's been some very interesting studies recently about how particular cellular automata can create forms which are very similar to ancient temples. And Actually, I've been working a little bit with a famous architect named Aisu Asoi, and she's very interested in using forms which can be created by folding up sheets in complex ways using parametric equations, and then changing those things into buildings. And that's a very interesting prospect. I've looked into similar things myself. That shape on the right was created by taking stacks, sort of taking repeated slices of networks and then tying them together to make a sort of pyramid shape. And also, I've endeavoured to try and make this connection between the computational mining and the 3D printing a little bit more real world by setting up a couple of online apps. So you can go on these apps, well, provided they're working. There's been some issues, but provided they're working, you can go on these apps and you can use them to, well, basically you just click on them, you can go through, you can tune up the shapes, select the rules, the runtime, etc., and download the 3D printable files. Then you can do what you want with them. You know, send them off to Shapeways, get them printed out of gold, whatever it is that you want. So I think this seems to be quite a nice idea to put out there, like programs which allow people to explore this space of forms for themselves and use these programs to create custom, unique, complex, beautiful objects. And you can make some pretty nice stuff with these kind of things. Here's a pen holder and a candle holder, and this other thing at the bottom here. This was printed out of ceramics. It was basically made with a cellular automata, with a little bit of modification. So this is just like a coin holder or something, but since you can print with ceramics, you could, make customized bowls and plates and all sorts of things. There's so much potential. And also, this American artist called David Allen Reese got in touch with me a month or two ago. He was interested in trying to use these cellular automata forms to create jewellery. I think that's another very interesting prospect. And there are very many other different kinds of things that you can do as well. I've been experimenting with creating forms sort of like the cellular automata, but not with a cubic geometry, with other kinds of geometries. And, I think, once again, these could be interesting for jewellery or aesthetics, but also they can have some very interesting structural properties. For example, if you have a look at that one on the left, it has this interesting feature that if you get a lot of copies of it, you can clip them together like Lego. There's many sort of interesting intricacies about the ways that these kind of shapes can form, the way they fit together and that kind of thing. And here, these are a load of other, a similar idea really. Take a network, evolve a cellular automata over it, and use that to delete some of the vertices and make it into something pretty. Well, I did that with this hoops ball, or C-sphere, which is something which I have been collaborating with the CEO of Hadron Sciences in the Netherlands, and he had this really interesting idea for this shape, and basically I found that if you take it and you knock away some parts, you can make some other pretty forms. So it could be another quite nice way to make jewellery, or potentially, things like lampshades. There are lots and lots of things you can do. Another potential application is making mobile phone covers. So, it's just so easy to generate these cellular automata patterns, and it doesn't really take that much work to make an app online where people can go and they can just decide, they can just use these rules to generate these really intricate, unique phone cover designs, and also perhaps manipulate them manually. And also, there's the thing about jewellery. So this is a bracelet, and this is my wife wearing this bracelet. And, this was generated by using a network as well. I think using networks is a really lucrative way of making 3D objects. Maybe I'm 2 seconds away from finishing. Literally 2 seconds. So I think this is a really lucrative way of generating objects. You can grow them using simple rules and 3D print the results. So that's pretty much the end of my presentation. Thanks for your attention. I've got a lot more to say about these things, especially the 3D printing stuff, that I'm wondering about maybe going into that in a deeper way in the future. But if anyone's got any questions, I'd be happy to answer.